Professor Ram?
Shall we start, Janki?
Yeah, we'll start. People join slowly. I'll start.
Mm-hmm.
Okay.
Yeah.
Hello, everyone. Welcome to the Department of Chemistry, IIT Delhi. Thank you very much for joining this webinar today. My name is Janikiram Vaitla, Assistant Professor at the Department of Chemistry, IIT Delhi. And we are very pleased to bring you this content today, which is a part of the online Pratidhwani series that the department is organizing. Under Pratidhwani, we invite eminent scientists from the different areas of chemistry from all around the world. These 30-minute talks are held every Thursday afternoon. Please do check out our webinar website. You can find the link in our flyer emails and also on department website. The webinar series is sponsored by OtherCafe. OtherCafe is an online platform that aids with the writing, collecting, organizing, collaborating, and publishing your research content through features and integrations with the products like Mendeley, Jotero, Orchid, Crossref, and so on. Think of it like Google Docs, special designed and developed for the academic community, and much more. Before we start the webinar, a couple of technical details. Please do not unmute yourself during the talk. If you have any questions, please type them in the chat box and we will try to get at least some of them to the speaker after the talk. Before we start the webinar, I would like to give a brief introduction about Professor Frenkel. Professor Frenkel received his PhD in experimental physical chemistry from the University of Amsterdam. After his PhD, he worked as a postdoctoral research associate in chemistry at the University of California, Los Angeles. After that, he was employed at Shell Research, the University of Utrecht, and the FOM Institute for Atomic and Molecular Physics in Amsterdam. He was appointed 1968 Professor of Chemistry in Cambridge in 2007. In 2011, he was appointed head of the Cambridge Department of Chemistry. Professor Frenkel focuses on numerical simulation on many body systems with a special emphasis on problems relating to ordering and self-assembly. Professor Frenkel is a member of the Royal Dutch Academy of Arts and Sciences, a foreign member of the Royal Society, and a foreign honorary member of the American Academy of Arts and Sciences. He has received numerous prizes and awards. He holds an honorary doctorate from University of Heidelberg. He is an honorary professor at the Beijing University of Chemical Technology and a conference professor at Nanjing University. Professor Frenkel is a world leader in the field of computer simulations of soft matter systems. He has made a seminal contribution to the methodology of simulation to predict phase equilibria and nucleation phenomena. Topics to which he has major contributions are free energies and freezing transition, entropic ordering in liquid crystals, phase behavior of polymer colloid mixers, lattice models for hydrodynamic transport, crystal nucleation, and the design of complex self-assembly by multivalent nanoparticles such as DNA-coated colloids. He has invented the configurational bias Monte Carlo method that has transformed the numerical study of chain molecules such as hydrocarbons. And he has created some of the most widely used techniques to predict solid-liquid coexistence. His contribution to computer simulation have been honored by both the APS Rahman Prize and by the EPS Alder CCAM Prize. Today, Professor Frenkel is going to give a talk on non-equilibrium phenomena and the nanoscale. A very warm welcome and over to you, Professor Frenkel.
Thank you very much. Let me see if it starts now. Must be the one. This. Let's see. Do you see something? See. So you see my screen?
It was not shared yet.
Oh, it is. Oh, that is curious. We tried it before, and then I try it again. I share again. And then I do this. Do you see
Now
my
it's
clip
okay.
now? Okay. And now I go to full screen mode for the presentation. Wait, it takes a while. Do you see this?
Yes.
Okay, so it's something should be moving. Wait, you're sharing your screen? Okay, that's fine. Yeah. Good. Okay, so thank you very much for the introduction. I will be giving a brief seminar today that, even though it's brief, is split up into 3 subtopics that are even briefer. And the main reason why I want to present these topics is because they are very simple, and you would have thought that we know all about it. And so the title of the seminar is really Non-Equilibrium Phenomena on the Nanoscale, and other things I thought I understood, because in working on the topics that I'll present today, I just found that there were fairly simple questions that either hadn't been asked or had not been answered. And so this is what I would like to share with you today. Now, here quickly, I give a list of people who have been involved in the research at various stages. I'm sure there are more, but these are the most important people involved. They're either PhD students and postdocs at Cambridge, or they're collaborators, the secondary collaborators at different places in the UK or outside. So let me start immediately with one phenomenon that is, I would say, popular in the field of non-equilibrium thermodynamics, but is becoming increasingly important in experimental studies of the nanoscale systems, and that's phoretic transport. Now, what is phoretic transport? If you look at fluid flow, then there's only a limited number of ways in which you can make a fluid flow. The most obvious one is that you apply a pressure difference between, say, one side of a pipe and the other, and then you get fluid flow. The other thing that you can do is to have an external force acting on the fluid. Like if you have gravity, gravity can make a waterfall flow. So it's clear that those forces can cause bulk flow. But there are other forces, if you wish, in thermodynamics that cannot cause a flow in the bulk. For instance, if you have a fluid and there is a concentration gradient in the fluid, then in the bulk, a concentration gradient cannot cause a flow. Also, a temperature gradient as such cannot cause a flow. I mean, the basic idea is that in a bulk fluid, the pressure equalizes very quickly, and once the pressure is constant, then these other gradients can't do anything, and they don't. But if you are close to a surface, then concentration gradients and temperature gradients actually can cause a flow. And those transport phenomena are called phoretic transport. And I will explain, first of all, why it is becoming important now. And the main reason is that increasingly people are looking at fluidic phenomena on the micro or nano scale. And so if you look at nanofluidics or flow in nanoporous materials, then the thing is that if you do the conventional kind of flow, that is the pressure-driven flow, then in a pipe you would have Poiseuille flow. And Poiseuille flow, if that's an exercise in sort of linearized hydrodynamics, the flow rate scales with the 4th power of the radius of the tube. Then, of course, if the tube gets so if you make the tube the diameter 10 times smaller, the flow rate goes down by a factor of 10,000. Now, if you have phoretic flow, if the tube gets smaller, the flow rate also goes down, but it only goes down quadratically. So you can see that even though phoretic transport is completely unimportant, if you look at flow in the water pipes in your house, it can be very important if you look at nanofluidic devices. very briefly, just a sketch of the effects. I give one example that is flow due to concentration gradients, and in a minute I will explain it. I'll give a very simple thermodynamic explanation for why it happens. But this is a situation where you have on the bottom, you see a solid wall, and there's fluid above it, and then these red dots are solute particles, and there's a concentration gradient. You see there's more to the left than to the right. And if the solute particles have a specific interaction, attractive or repulsive, but a specific interaction with the wall, here it's attractive, so there's more particles close to the wall than in the bulk, then a concentration gradient in the bulk, although it cannot set up a flow without the wall, can set up a flow. And the flow profile is very different from the Poiseuille flow, because the flow for velocity is zero at the wall. I assume that there's non-slip boundaries. And then you get a very sharp, very thin shear layer, comparable in thickness to the range of the interactions. And then in the bulk, it's constant. So this constant flow velocity is called plug flow. And this is typical for phoretic phenomena. So you get flow that is induced by a concentration gradient, but only in the presence of a surface that interacts with the particles, the solute particles. Now, there's another phenomenon that I will briefly mention, although I will not go into much detail today, and that is the thermocapillary effect, which is basically the same thing, but now you apply a temperature gradient. And so here the concentrations are the same, but these particles are cold and these particles are hot. And it's, again, typically, if you have a specific enthalpic interaction between the wall and particles, so you can think of some interaction energy, then you get a similar flow pattern. And as I said, these effects become really important if you talk about nanoscale phenomena. And so in recent years, there has been a lot of interest in these transport phenomena, also because there has been much research on active matter. And I'll come back to active matter in my second part, the second part of my talk. But there you'll have also gradients that cause flow phenomena, and they may be concentration gradients, they may be thermal gradients. So people who study active matter always say, oh, due to the concentration gradient, you get a flow velocity, but then they never compute how much. And the reason why they don't is because it depends on the details. And so most of the people working on these problems come from the physics community, and they don't like the molecular details so much. But I'm a simulator, so I thought we should be able to compute this. And so, as I said, you need the surfaces, you need the interaction with the surfaces. And so we have to know about the interaction with the surfaces to compute the flow. And that is what is going to cause the flow. But the first thing I will do is to explain very briefly the thermodynamics of the whole phenomenon. And I start with a relation that I'm sure that in principle you know, but many of you may have forgotten. That is the Gibbs-Duhem relation. And the Gibbs-Duhem relation basically relates the variation in the pressure of a system at constant temperature to the variation in the chemical potential of the different species. So that's basically, it's a very simple derivation, but in essence, it means that if you have gradients in the chemical potential, you could have gradients in the pressure, except that in the bulk system, you don't have a gradient in the pressure, because very quickly in a bulk system, as soon as you have a pressure gradient, the system will rearrange its density, and that goes at the speed of sound. So it goes very quickly. And then the pressure gradient in the bulk is zero. And that means that you have a relation between the gradients of the chemical potentials and the density. So the rho I, the density, is simply the number of particles Ni divided by the volume. So this is what you have in the bulk. And in the bulk, therefore, the chemical potential gradients are simply related through this expression. Now, the thing is that you can do something very similar close to the surface, except that there the density will no longer be this bulk density, because you have a specific interaction that either attracts or depletes solvent particles, the solute particles. So what I assume is actually now that we have a chemical potential gradient along the surface, but that perpendicular to the surface, the chemical potential is effectively constant over the very thin layer where phoretic flow is created. So the chemical potential does not depend on the height above the surface, only on the distance along the surface. So that's what we get here. And actually, because it doesn't depend on the distance from the surface, it is actually equal to the chemical potential in the bulk. So the chemical potential is at a constant distance along the surface. It is constant at the surface, and it's the same at that value of x in the bulk. But the thing is that although this is constant, the density itself, so the chemical potential is related to the density and what's called the excess chemical potential. The excess chemical potential is everything that is due to interaction. And so even though this is constant, it doesn't mean that these individual terms have to be constant. And in particular, if you have an interaction with the surface, which changes this, then you'll also get a change in the density. Now, if you then look at the pressure gradient at the distance z from the surface but close to the surface, then you get a relation between the chemical potential gradients. And now the thing that enters here is not the bulk density, but the local density. And because the local density is not equal to the bulk density, you can get a non-zero pressure gradient close to the surface. And that is actually what's causing the flow. And so here I just subtract the bulk density to make it a bit more visible. So if I did, because with the bulk density it's just zero, and so you see that the thing that is important is the excess density, is the difference between the density near a surface and the density in the bulk, and that multiplied by the chemical potential gradients. So then the next thing is that actually, if you then want to know the flow, you have to solve, in general, the Navier-Stokes equation. But because we talk about flow at very low Reynolds numbers, so the typical dimensions of the system are small, the viscosities are high, and so you can use the Stokes equation, which is the linearized version of Navier-Stokes. And this is a relatively simple equation to solve if you have an expression for the pressure gradient. And from these thermodynamic arguments, we do have an expression for the pressure gradient, and then you can compute these flow profiles. Now, I will not go to the actual calculation.
Bro, you may be the
Sorry? Hello? Oh, was there a question? Or?
No.
Okay. No, anyway, so the main thing is that this kind of expression for the flow near a surface had already been worked out a long time ago by people like Derjagen. And it's a macroscopic argument. So you use macroscopic thermodynamics, you use macroscopic hydrodynamics. But the thing is that these phenomena all happen on a scale of intermolecular interactions, so maybe 1-2 nanometers. And so one question is whether you can actually use this kind of argument on a nanoscale. And that is something that is not at all obvious. And so what we initially thought is, okay, in simulations, if you do, for instance, molecular dynamic simulations, you can also compute the pressure in a system, and there's different ways of doing that. And we thought, okay, the only thing we'll do is we do exactly the same thing, but now we compute the pressure close to a surface, and we see how that pressure changes with density or with concentration, and then we can compute the flow velocity. And the answer, as I'll show you, was no. That does not work. And as an illustration, I will give this diffuser capillary flow near a hard wall, or it's actually a Lennard-Jones particle wall. And first of all, I want to show that it is important that you have a microscopic description, that it makes a difference. And so the first picture I show you is just a result of a simulation that we obtained by simply imposing a concentration gradient. So we just had a system, we had a high concentration on one side, low on the other, and we looked at the resulting flow due to the specific interactions of solutes with the wall. And this is what you see. So actually, in this case, the flow velocity is negative. And depending on the concentration gradient, if it's very small, you get a very small flow velocity. But you see this typical plug, like so a shear layer and then a constant flow velocity. That is what you get in those cases. But there's also something that you can never get if you have a continuum description, and that's this. We get an overshoot. And if you assume that you have actually a constant concentration gradient and a constant viscosity, then you in any thermodynamic and macroscopic theory would give you a monotonic profile of the flow. So the fact that you see this already indicates that the microscopic details are important. Now, the next thing that I want to say is how can we compute these things? So rather than every time doing a non-equilibrium simulation, we thought maybe if we can compute the pressure gradients or the stress gradients in the system, we can compute the flow. And the problem here is that if you do numerical simulations, the flow is not uniquely defined, and so there's different definitions. They all have different expressions, but they all, when people used it in the past, they were worried about it. But then they found that you can use these expressions to compute, say, the surface tension, and they all give the same answers, but they don't give the same phoretic flows. And so this is where we did our simulations to find out which correct expression is correct. And the answer basically, as I'll show you, is none of them. What we try to do is actually to compute the force on a particle directly in a non-equilibrium simulation, and see what the forces are that act on particles. Now the thing is that actually is impossible. And the reason why you don't see any forces on particles, that is in steady state, particles undergo no acceleration. And therefore F equals m times a. It means that there is no flow. There's no force. But then we did a trick in the simulation. This you can do is basically by making the mass of the particle a tensor in such a way that the flow along the surface was completely suppressed. And then you actually can measure these forces. And that is the result I want to show you, because there we can see that these microscopic expressions for the stress don't work. So this is an example where we have computed the force per particle as a function of the distance from a wall. And this is a very crowded picture, but you see four curves. One is the direct non-equilibrium curve. So that basically is we apply a concentration gradient and we look at the forces, and that's these blue dots. The red and the green here, or the green and red here, these curves are what you get if you use microscopic expressions for the pressure. And you see that they're completely wrong. So none of them actually works. The only expression that seems to work reasonably well is the one where we assume that you can compute the force from a kind of local excess expression where you couple the concentration gradient. In this case, it's actually a temperature gradient, but when you couple the gradient to the local axis, so we compute the axis, we compute the local axis, and from that we compute the flow velocity. So it seems that that picture is correct, but what anybody in simulation would do, namely computing the pressure gradients, is incorrect, and that is something that could have been known a long time, but to my knowledge was not known. So that basically it means near a surface, you cannot compute the force from a stress gradient. I think that here, if you wish, I can take your questions before I go on to the next topic. But you can also ask questions at the end. So that's I leave it to the moderator to decide how to best do this.
Probably.
Otherwise, sorry.
They will ask it later.
Okay, fine. Because the next topic is related, because it has to do with active matter, Janus particles. So as you know, Janus particles are these particles that, well, they may be spherical or non. So you have a spherical Janus particle. One side is coated with a non-chemically catalytic surface. The other side is catalytic. And for instance, one of the better known examples is where you have a colloidal particle. One half is coated with platinum, and you put it in a solution of hydrogen peroxide. And on one side you get a reaction, and as a consequence, the particles move. Now the question is, why do the particles move? And there have been many different possible explanations. The most commonly used explanation is that you have diffuse phoresis. So that's what I was discussing before. You have a concentration gradient along a surface, and that induces a flow. So why is there a concentration gradient? Well, if you have a reactant and it reacts here, then the yellow species disappears, so that the concentration here is lower than there, and then you have two new species that appear here, so the concentration of these is higher, and that could in principle give a flow. The other possibility is that you say, well, the reaction creates heat, and therefore you get a thermal gradient, and again, then you get to the thermophoretic flow, and there's even a possibility, if there's electrical charges involved, that there's electrophoretic flow. But I mean, I will not go into the details of these different theories. There's been a lot of work. There's an article that you see that has reviewed these different methods. But the interesting thing is that one particular mechanism had not really been discussed, and that's something I discussed when I was at a workshop in the U.S. In Santa Barbara, and from a distance you could see these SpaceX rockets being launched. Actually, it was almost 100 kilometers away, but you could still see it quite well. It's very, very beautiful sight. And I was discussing this rocket launch with Wilson Poon, who is, as you may know, a great experimental colloid physicist. And he said, did you know that for all these catalytic particles, the Janus particles, that they all use rocket fuel? So actually, I showed the example of hydrogen peroxide, but they also use hydrazine, and so they're typically rocket fuel. And so we thought, well, but maybe the colloids don't use phoretic propulsion, but they use rocket propulsion. That's a fairly obvious thing to ask. But apparently, we looked and we couldn't really find much evidence that people had been looking into that. And so we did some simulations, a very simple coarse grain simulation, where we made a colloid and we put a small reactive patch on one side. And then in addition, we made sure that there would be no diffusiophoresis, no thermophoresis for electrophoresis. I mean, I will not go into the detail how we could switch all these other things off. So, but basically, it was a way in which all the standard effects were completely suppressed. And then what we did is we have reactions taking place here where a pair of fluid particles essentially at some point get an extra energy of about 1 electron volt, which is corresponding to hydrogen peroxide in water. And this fluid has the same properties as water, so it was modeled as water. And this mechanism of propulsion is not normally considered in the theories of this active matter, because hydrodynamicists don't look at the situation where the flow profiles haven't developed yet. They assume that flow profiles are basically immediately there and the fluid is incompressible, whereas in reality, that is not true. And so we actually did a simulation and then looked at how fast the particle would move. So this is, as you see, the mean square displacement over 6 times the time. That is effectively the diffusion coefficient. And so if the particle is diffusing, then this ratio should go to a constant. But if it's actually moving with a constant velocity, then this should be going up linearly in time. And this is what you see. The blue curve is what you get with no reactions. And so you see, indeed, it goes to a constant, which is then the diffusion coefficient. But as you switch on the reactions, this is the reaction rate. And so this is the highest rate and this is the lowest rate. You see that clearly the particle moves, and it moves linearly. So this is precisely what you would expect if the reaction drives a propulsion. And in this case, as I said, it cannot be diffusophoresis, it cannot be thermophoresis, and it cannot be electrophoresis, because all these effects are not there. So, I mean, we found that really interesting. We checked also if the velocity is linear in the reaction rate, and it seems to be quite linear. The other thing we tried to check is what we want to know is the numbers that we get out compared to experimental numbers. Are they relevant, or is it just orders of magnitude too small? And we tried to express this for a 1 micron colloid that people have been studying experiment. But we estimate that the order of magnitude of the velocity, because it actually details a lot on the topography of the surface. But in our case, we found that it would predict speeds of 10 to 20 microns per second, which is actually very comparable to what people see in experiment. Now, it doesn't mean that in experiments people see this mechanism. It just means that you cannot rule it out a priori. You have to consider it. Now, the one test, of course, is can we distinguish this reactive propulsion, where it's really momentum transfer to the colloid, and then the opposite, an equal momentum transfer to the fluid that moves the particle or not? And you can check that by looking at how the velocity depends on the energy released in the reaction. Because if it's diffusion-phoresis, it only depends on the species. Therefore, the energy release is unimportant, so it shouldn't depend. If it's thermophoresis, then it's proportional to the heat, and therefore it's proportional to the energy release itself. Whereas in the impulsive transfer, it should go as the square root. And if you look at the figure that we then computed, so here you have the momentum transfer per unit time, and you see that actually it scales very nicely with the square root. Well, very nicely. It is noisy because these are small phenomena, but it scales nicely with the square root of the energy release. So this is one other indication that we have about the importance of direct momentum transfer in these active matter particles to drive the propulsion. Now, I would be very happy if people would test our predictions, but until now, I think there are no experimental tests yet that have been distinguishing these different possibilities. Still, that would be possible because if you play with the shape of a colloid, so you don't use a spherical colloid, but for instance, a colloid that is a concave part where you can partly shield the reactive area, then these different mechanisms should work very differently. So I'm very sure that these are things that are experimentally testable, and I would be incredibly interested if people would do that. So that's the second part of the talk. So we've gone from phoretic transport past surfaces to actually propulsion of particles, in this case by chemical reaction. So in this case, the propulsion is not phoretic, but by impulsive momentum transfer. The last thing I will discuss, and maybe I'll go on and then you can ask questions, Dale. The last bit I'll discuss is something that is, in a sense, simpler and more unexpected. And that is something that I will call soft matter monopoles. Now, you know that, there are many countries in the world that invest many billions in searching for elementary particles. So I have here a picture of CERN, where they have these huge detectors, and this is the Japanese neutrino detector. So these are very, very large experiments that people do to either study the properties of known elementary particles or to detect new ones. And it's expensive. And so basically you need you need more. You need more like this. You need huge budgets to do these things. But there is one odd particle out. And that has actually been of much interest and has never been found. And that is magnetic monopoles. Now, as you may know, there was an experiment in the early 1980s at Stanford, where somebody called Blas Cabrera was looking for magnetic monopoles. So he had set up a loop, basically a loop where he would look at the electrical field induction if a magnetic monopole passed through the loop. And actually on one evening in 1982, he found on his detector, it was one of those old chart detectors, he found one event that was perfectly fitting with what people assumed that the magnetic monopole would do. So everybody was wildly enthusiastic. And so actually this resulted in a publication in Physical Review Letters that contained a single figure, namely the picture of the chart recorder with the single event. So it was probably the only example that I know of where people publish a single event in a journal. And the only problem was that, of course, then everybody started looking for this magnetic monopole. And so in particular, Blas Cabrera got a large grant to build a better detector, and other groups got a lot of money, but no similar event has ever been recorded since. And so actually that was, of course, a big disappointment. And actually, Blas Cabrera at some point stopped the magnetic monopole research. And I thought, so maybe he's now going to look for something that is a bit easier to detect. But that is not quite true, because apparently what he's working on now is cryogenic dark matter search. So he really likes to look for things that are not so easy to find. But okay, that is his choice. Now, although monopoles were not discovered until now, at least, as elementary particles in their own right, there have been experiments in the past the 10 or 10 plus years, where people have found monopole-like excitations in hard condensed matter. And so in particular, there are materials that are that is like they're called spin ice. They're locally antiferromagnetic magnetic materials where you have four spins in a tetrahedral arrangement around the particle. And if the arrangement is such that there's an equal number of spins pointing in and out, then it is like neutral. But if you flip a spin, then in some ways, but not in every way, but in some ways, it behaves like a magnetic monopole. So there have been very extensive studies. So there's a paper in Nature, and there were lots of papers in other high impact journals where people have been looking at these magnetic monopole-like excitations in hard matter. And so the question I would like to know is, can we see magnetic monopoles in soft matter? And I will argue that the answer in principle is yes, although in practice it may be a bit difficult. And what you need is a colloidal suspension, you need a heat source, and you need some patience, a lot of patience probably. But okay, and I'll explain how this works. But in order to explain that, I will actually use as an example not the magnetic monopole, but an electric monopole. Of course, there are electric monopoles, but just suppose, can we have a situation where an uncharged particle starts behaving as if it has charge? And the answer is yes, and the reason is equilibrium thermodynamics. So this is where the non-equilibrium aspect comes in. If you have a polar liquid of molecules with no inversion symmetry, and that basically means that if you invert the molecule, that then the properties change. So for instance, if you have a water molecule, then if you flip the dipole moment, then that's no longer a water molecule. So the molecule has no inversion symmetry. And in those liquids or those fluids, molecules with no inversion symmetry, if you can show that a heat flux will create polarization. Or actually, what you can show is that there is no symmetry argument telling you that there should not be an electrical polarization. And this is implicit in the work of Onsager already, but there was a more detailed study by Fernando Bresme and Dick Bedeau and Signe Kjelsop about 12 years ago, where they went through the arguments to show that really, if you were to apply a thermal gradient in a beaker of water, that you should get a weak electrical polarization. It is weak, so I think it has not yet been observed experimentally, but in principle it should be there. And so basically the argument is that the polarization of the fluid is proportional to the temperature gradient. Then the next step is that because you have no free charges, in this particular case, the dielectric displacement is zero. So because that, for D, the sources are charges, or true charges. So D is zero, and then you get that the electrical field therefore is related to minus the polarization. So so if you have a temperature gradient, you get a polarization, and therefore you get an electrical field. Okay, that's step one, and that is something that follows very directly here. The second thing is, now suppose that you put a neutral particle in this fluid and you heat it. So this is a colloidal particle. It has been heated, and at the surface of the particle you have a particular temperature that is higher than the bulk temperature. So as you move away from the particle, the temperature goes down. And how does it go down? Well, actually, it is determined by the heat transport equation. So you effectively have to solve the Laplace equation in the bulk of the liquid, and you get that this temperature decays as 1 over r to the bulk temperature. So that's what you see here. The temperature at the distance r goes as the temperature in the bulk, and then something that goes as 1 over the distance. This is the radius of the colloid. This is the distance. So that precisely at r equal to the radius of the colloid, you have the temperature at TR. So that's trivial sort of solving of the Laplace equation. And so that's what in heat transport is called Fourier's law. So it's a linear law. Okay, so now we have a temperature gradient, and then we can say, well, but we know that the electrical field should go in water at least as the proportional to the temperature gradient, and we have the temperature profile. So therefore, the electrical field should go as the gradient of this. So here's the radius, so it goes as something that goes as 1 over r squared. But now you have to think of your first year electrostatics. If an electrical field goes as 1 over r squared, then you can look at the flux of the electrical field through any closed surface around our colloid, and it's constant. It doesn't depend on the radius. So this behaves as if there is an effective charge. And so by heating a colloidal particle in a fluid of particles with no inversion symmetry, you can get actually something that behaves like a monopole. Now, in this example, I took electrical dipoles. In principle, you can do the same thing with magnetic dipoles, but it's a bit harder to make the systems where you have particles with no inversion symmetry and an embedded dipole, and that's basically because the dipole magnetic dipoles have a different time inversion symmetry than the structural part of the particle. So yeah, you need some tricks, but in principle you can do the same thing for magnetic colloids as well, which would mean that if you have a heated colloid in a fluid of paramagnetic particles with no inversion symmetry, that it should behave in some ways as a magnetic monopole. And so, as I said, the experiments are not easy. So we did a simulation, my student Peter Winsberger, where he took two particles. One was heated, the other was cooled, and then he computed the electrical fields that result. And actually, this is periodically repeated, but we can see here is the arrows are the local polarization the local field that he measured in the simulations, and the curves are actually the results that you get if you assume that this is just a periodic array of point charges. So you see that the observed pattern of the field agrees very well with the assumption that these two particles, even though they are neutral, behave as if they carry a charge. And so that I find really extremely interesting, because you can use the same thing for a heated particle or a cooled particle in a molecular nanocolloid. And then it basically means that, yes, it should be possible to make soft matter monopoles, and all you need is the correct colloidal suspension, namely of the paramagnetic particles with no inversion symmetry and a frozen in magnetic dipole moment, and you need the heat source to heat the particles, or if you can, to cool the particles. And then, of course, what you do need is very, very careful experiments, because the total charges that you get, although they are certainly there, they are small, so they're of the order of a single electron charge, and it's extremely difficult in experiments to control the charge of colloids to better than a single charge. So you really want the colloids to have no charge of their own at all. So that makes it a difficult thing to do, but that is something that I think is very interesting. And this is actually where I'd like to stop and to take questions. So thank you very much.
Sir, this is very information season, sir.
Sorry?
This is very useful information season, sir.
Okay. Shall I stop sharing the screen?
Sir, my name is Prabhakaran, sir. Prabhakaran.
Janki, would you mute?
I put it mute. Yeah. Sorry, Professor Frenkel. So thank you, Professor Frenkel, for the insightful and stimulating talk. I hope many students and faculty enjoyed your talk and understood non-equilibrium phenomena on the nanoscale. It was interesting to see how other effects are dominated transport phenomena on the nanoscale. You have given very nice examples and also these unexpected and exciting results on nanoscale transport simulations encourages many young researchers. There are some questions in the chat box. Shall I proceed?
Sir, I have doubt, sir.
Prabhakaran, could you type your doubt in a chat box?
Okay, sir. Okay.
The question is from Professor Ram. How does this apply to the flow in capillaries? Example, blood flow through veins. Professor Frenkel, you are muted.
This is better, I hope. I think that when I stop the presentation, okay, good. So how does it affect flow through blood, the blood flow through vessels? I think that so even very small vessels are probably sufficiently large that these effects are there, not very important. But where it is important, I think, is in the many much narrower channels that you have in cells. So, of course, in the cell membrane, you have ion transport channels and other channels. Typically, those are so narrow that you don't really have coupling between hydrodynamic flow and particle transport. But there's also larger channels like the aquaporins, etc., where you really talk about things that have diameters of the order of nanometers. And I think that there, all these coupling effects must be present. And I think they have not really been investigated very much. So I'm sure that in biological systems, these phoretic transport phenomena are much more important than people may have realized. But I'm not aware of any systematic experiments.
Janki, if I can just ask a follow-up question to that, Daan. My interest is also, because the surface is not a static surface. Typically, in biological systems, the surfaces themselves have, they contribute either energy or motion or something. So, any comment?
Well, I mean, the thing is, as soon as the surface itself is active, I mean, so, well, the first thing is that I haven't really considered that aspect, but it is certainly true that if you get in addition active surfaces, then I think that you can expect that the active surfaces will drive the flow of particles, but they also will influence the transport of say species of chemical species and of energy. So I think that these coupled transport phenomena are going to be probably even more important as soon as you have also active surfaces. But I think very little is known about that, so it's a really interesting subject.
Okay, Professor Frenkel. So there is another question. Ram, do you have any question? Okay. So there is another question from Aniruddha still. So his question is in the second part of your talk on Janus particle, could you explain how do you switch off the interaction due to the three mechanisms other than yours?
Sorry, how do I, at the last bit, can you repeat that?
Could you explain how do you switch off the interaction due to the three mechanisms other than yours?
Okay. Yes, very good. Yes. So I said we can suppress diffusophoresis, thermophoresis, and electrophoresis. Well, the last one is easy. There are no charges in our simulation, so that's gone. The thermophoresis is we actually use dissipative particle dynamics, and in dissipative particle dynamics, you have the option of actually imposing a thermostat in the fluid, so that there is no so temperature gradients are immediately suppressed in the fluid, and so we could make sure that there would be no temperature gradients in the region on the side of the particle where it could drive flow. So that's the way we suppress temperature gradient. The final one is concentration gradients, but actually the way we drive the reaction is not by actually making new species, but only by locally releasing energy and therefore also momentum in the fluid. But there is no concentration gradient. So all three of the phenomena I discussed cannot occur in the model that we used.
Okay. There is another question from Azaz Ahmad Mir. His question is can we get a negative refracting index medium using active matter?
I would say I don't know. I mean, the thing is, it's I would think that typically in order to get negative refractive index like behavior, you have to do something with the polarizability of the medium itself. And so I think that active matter is probably not the first route that you would try under those circumstances, but maybe other people have more original ideas about that. It's certainly something that I haven't thought about, and so I wouldn't really know the answer to that question.
The next question is from Professor Pramit. How do obstacles acting as heat sinks or heat source affect the flow? That is, will local temperature gradients matter?
Yeah. Yes. Well, I mean, this is actually a very interesting and tricky question, because if you look at non-equilibrium thermodynamics, it usually is expressed in terms of the macroscopic temperature difference. So, for instance, the second law of thermodynamics, you look at the heat flowing in out of a system at one temperature and the heat flowing out at another temperature. But then if you want to transform that to a local effect, you effectively have to use Gauss' theorem to actually express everything in terms of local gradients and local flows. But if you use that language, then local sources and local sinks actually can also contribute to the flow phenomena.
One last question from Jill Thacker. Just he would like to know that what is a Janus particle?
Okay, so a Janus particle is a particle that has, first of all, it's called Janus because it has two phases. One side it phases, for instance, platinum, and the other phase is maybe palladium or polystyrene. So the word Janus is because the Romans had a god called Janus, and he had two faces, one at the front and one at the back of his head. Or I guess that if you have two faces, distinction between front and back is difficult. But it's a two-phased particle. And so that's why it's called a Janus particle. And the way people make these particles is typically by having some colloid and then using and having them on the surface and using deposition techniques to deposit a metal on one side only, so that you get an asymmetric, so chemically asymmetric particle.
Yeah, there are no more questions on the chat box. So
Okay.
I would like to thank Professor Frenkel for taking some time out and agreeing to give this webinar for faculties and students. Professor Frenkel, we would also like to host you physically in our institute sometime.
I would be delighted.
Yeah. So there is small information to the students and audience. Our next talk of the series will be delivered by
You've gone mute, Janki.
Sorry. Yeah. Yeah. So the information is our next talk of the series will be delivered by Professor Annabella Celloni from Princeton University on 3rd December at 7 p.m. So the links to join the webinar will be available on our website, and students are requested to register to avail for certificates. We will provide special certificate to students who will attend at least 10 talks of this series in a year. Finally, I would like to thank Professor Anil J. Ilyas, our HOD of the department, and Professor Ram Ramaswamy. He is giving an excellent guidance to us for conducting this webinar series. And also, I would like to thank Dr. Somik, who is the main coordinator and a key person for this webinar, and also Dr. Bishwarup, who is the co-organizer. With that, I'm concluding this webinar. Once again, thanks to all of you. We hope to see you all soon. Have a great evening. Okay.